So this is kind of the summary of everything that I'm going to talk about, and I'll get back to this at the end. But basically over here we've got the USGS in green, and mineral resource themes, sort of study or research themes that the USGS has been involved in since the beginning of our agency. It was really the reason that USGS was founded. Go survey the west of the United States and see what's out there in terms of resources. So we've been working on figuring out what is a mineral resource. They exist inside of ore deposits, of mineral deposits, which is an area, volume of earth where there's a concentration of some material. In this case, we're going to focus on non-fuel resources. So some material that's not a fuel, that's of some inherent value. So resource is something that's concentrated enough to be economic for extraction. A deposit, though, is an area of earth, a volume of earth where there's a concentration, but it may not be economic. So these are important concepts when we think about seeing them from remote observations and things like that. But we've been worrying about that for a long time. We've been quantifying within those deposits what are the resources, how much, and things like that. That's assessment. Of course, there's exploration. How do we find new ones? There's actual mining. That's grayed out because we actually stay away from that. We're trying to be a non-partial science agency, and we don't do the actual mining stuff. Reclamation, though, we've been involved a lot in basically assessing what things ought to have looked like in terms of the rocks and soil before the mining and how they should look at the end. So we basically assess often what the impacts of the mining has been after bad things have happened, really. And then there's this bottom part, the stocks of resources, the flows of them around the world, and the use tracking. This is in our National Minerals Information Center. And that's basically all they do is for every resource, there's also an interchangeable word, commodity. And these tend to be elements, but they can sometimes be minerals. So it's quite confusing, as Angela knows. We've been talking about chromium and chromite, and it's confusing. But often it's just an element like aluminum or gold or palladium or tellurium. And they'll track it every year. Where is it? How much do we have? We being the U.S. Who's making it in the world? What's the limitations, the suppliers, the producers, primary, secondary, and so on. So that's a really big part of what we do, and that information, arguably, no one else in the world produces these mineral commodity summaries the way we do. And so then there are the various sort of scientific expertise in our agency that I sort of tried to draw these bars as to where they pertain. So of course economic geology, mathematical geology, across the whole board really. But environmental geology and these carbon studies actually is something that we'll get back to. Really important for the mining and reclamation part. Natural hazards work, as it'll be a theme that I'll get back to, that the intersection between mining and hazards, the hazards associated with mining, specifically tailings dams failures and the potential for movement of large amounts of debris, not just from a tailings dam failure, but from historical deposition back when mining wasn't regulated. That's a serious issue for our country, and certainly a big one around the world. Over in NASA, I try to do the same thing for other agencies, to try to show how we can overlap in the ways that I've seen. And so I saw what I'm calling data science, just understanding big data sets, machine learning to draw knowledge out of them. This is something, again, that can go all the way down. We've been talking about it and the little stuff that we're doing, but I think it has a lot of, in terms of ore deposit models and classifying them, and exploration, bringing together these huge data sets and then trying to figure out where the new deposits could be. That's an area where neural networks have been explored in the 90s a lot within the USGS, and then it sort of dropped off. And we were talking to the sort of USGS guru of this work, Don Singer. He's emeritus now, but he's in Menlo Park. And he was kind of excited about, get these NASA folks doing deep neural networks and stuff. I don't know about that. That's far beyond my area, but that's one thing that people have seen could overlap. Obviously, a lot of the remote observations that you all do in these instruments, the spectral and hyperspectral, the INSAR, I've seen many applications across exploration, obviously, but also in these areas of mining and reclamation, I think, and the issues of disaster mitigation, again, being able to observe around the world, because most of mining is happening outside the United States, the big mining, the big deposits that can cause disasters, and doing spatial analysis of this type of stuff. The other project that I'm working on with Lynn Rothschild, obviously, is this, I guess it's the space bio folks that she's involved with, the synthetic biology and rational design. And then this Intrinsics is a contractor here on campus. I don't know how many of you know of Intrinsics, but we are very interested in what John Freeman with that company is doing with phyto work. And so we'll try to touch on some of that. So why now? Why all this? Why now? I said, why mineral resources? Why now? Well, there's a whole bunch of things going on in our agency. We're sort of governed by the executive branch, so when the president says do something, we have to jump around. So when there was this executive order about critical elements, sorry, that was from the Washington Post, about overlapped, says we need to expand because of the National Minerals Information Center I mentioned. They produced this criticality index that showed which of all these resources the United States was in danger of running out or being squeezed out of supplies. It's not really that these things don't exist, but for various supply chain and distribution reasons, we could be vulnerable. And one example is this element rhenium, which has very few uses, but it's a super alloy used in defense applications, and it's just very limited production and supply, and it would be easy to be vulnerable. So President Trump says we need to expand, and these things need to be made in the United States, because hardly any of them are. You know, we have mining in our country, but we don't do a lot of the critical minerals production for various reasons. So his order drove the Department of Interior order down here in this corner. Oh yeah, that's good. Anyway, down there in the lower right, about this criticality, and so we're being driven find critical minerals in the United States. Okay, do more mining in the United States. Okay, but there's also, there's issues with that. That's where we're coming from. Where you all are coming from, you've got a call out right now about disaster risk reduction. We're trying to prevent disasters. Okay, we're talking about the HISPIRI. Am I always saying that wrong? Some opportunities to use some new instrumentation or pursue some hyperspectral data sets that we haven't pursued before. Certainly there are folks in the USGS that do a lot of mineral mapping, but those are some things that I see as driving, why this now? Why do this now? So let's get into some of these critical elements, which I'm switching now, and calling them byproduct and co-product. And this wheel is trying to show that basically we've got the primary mined elements here. Let's just focus on copper, because copper mines are ones that we do have in this country quite a bit. And then we have co-elements that have their own production, and the white especially is the critical band. These elements that have none of their own mines. They're only produced as a secondary processing stream of one of these main mine types: copper, zinc, big ones, for gallium, indium. These are some of our main critical elements that are on this list. It's even trickier than that, because not every copper mine that has tellurium, for example, will actually extract the tellurium. It may not be economic for them to put up a whole nother infrastructure to extract the copper. So the production of these elements in white is tied to the production of the main element. If copper is not of high value and copper production worldwide tails down, then our rates of production of those critical elements that come from copper mines will also go down. And the reason of that is that production of these guys is usually just a tiny fraction of what they're making in terms of money. So it's hard to influence, to push this system just because President Trump says we need more tellurium, well, we can't just go out and mine more tellurium from the tellurium mine, because that's not how it works.
Andrea, I don't see gold on there as a primary carrier. Is that?
Yeah, I guess there are plenty of gold mines, but gold does show up in these. It says that also have considerable own production infrastructure. So I don't know. We have plenty of gold mines in the United States.
Yeah, usually the silver is a byproduct of gold mines, not the other way around.
Yeah. Well, Europeans, I don't know. So moving on right into this project that is the USGS funded side of the collaborations that we're doing. And I think I'll switch sides again. We're calling it Biological Solutions for Sustainable Mining. And like I said, it started this year. It's got a 3-year lifespan. It basically is employing 2 full-time postdocs. There's 3 postdocs on the project. 2 of them are working closely with me, and they only get half of their salaries. And the other one will be working with Len Rothschild, as we'll talk about. So the idea is to use biological or biologically inspired methods, we'll talk about what that is, to help with mining. And I said originally USGS doesn't really do mining. But here, because in part of the executive order to enhance critical element production, if we can come up with a way to extract critical elements that does not require a whole nother processing infrastructure, it's not energy intensive, it will be more beneficial for companies to mine them. So that's something we're going to work on. I'll talk about in a minute. The other thing that we want to do is improve mine land reclamation. And this comes back from my experience in the mining, being in mineral resource program, which I kind of skipped over, but I'll get to it as I go along here. I've seen a lot of historic mining here in California that was unregulated because it was way back in the gold rush times. So we want to basically enhance the development of soil. After mining, all true soil is gone in most of these surface mine. So you just have sediment. So you basically need to reestablish soil. So it happens that I've been working for the past 2 years with a postdoc in the area of carbon sequestration, doing what I normally do, which is look at micron scale reactions of minerals and microbes and how they react with carbon. All that really applies now to enhancing soil development. We also want to reestablish native vegetation. So a lot of times at mine reclamation, they'll just go in and let's plant some kind of fast-growing plant that doesn't even come from this area. And it doesn't support what we call ecosystem services. The birds can't use it, the bugs don't eat it, and so on and so forth. So we need native species. And the sediments that often are associated with mine wastes are not easy for plants to grow in. They tend to be highly acidic and hard. So this is a struggle, and we're going to be working on that and doing some basic research. That's C, I'll skip that. And those are the 2 postdocs that I'm working with on that. And John Freeman that I mentioned at Intrinsics, he has some fun bacteria that we're going to be using to help with the plants establishing the native vegetation and so on. So we'll get to that. And then I'm really in charge of this bottom part, which is basically doing some sustainability calculations. This might seem like a weird thing, but this 3 little bubbles are basically showing what sustainability means to corporations these days. It's 3 pillars or whatever they call it, but it has economic factors, social, and environmental factors, and they're all interdependent. Obviously, if you just take water at a mining concern, how much are you using? You're taking it away from the people that live nearby. Are you polluting it? Well, they're going to be mad. Just things like that. And how are you drawing down the groundwater? These are real issues, for example, in the western United States. So it's not that we want to come up with one number here, but we want to show people that adding these biological solutions really does provide a value for the mining company, that it's in their interest to do these things. It's not a punitive thing. It's going to enhance their bottom line. That will get them to listen. So porphyry copper, as I mentioned a few times, it's one kind of copper mine. They're very important in the United States. It's a really fuzzy picture of kind of the state of Arizona with these way too big circles. I didn't make it, but it's showing where the porphyry copper mines are. There's a lot of them, and they are big. And these other pies are from a recent report on tailings dams failures, and I don't want to go all through it. But basically it's saying this is the ore coming out of the porphyry copper deposit. This is what's actually economic from it. You know, they're using lots and lots of water, and they get down to a little concentrate, the value. You know, you end up with just lots and lots of waste, solid waste and liquid waste. And that's particular for porphyry coppers. And they're a big sustainability challenge, so that's where we want to kind of focus our work because they are in the United States and so on. So one of our, the field site where we're doing any field-based part of our work is in the Patagonia mountains of Arizona, unfortunately, not the fun ones. It's near Tucson, and there's lots of mine waste and stuff like this typical, well, yellow boy, they call this kind of mine drainage, very acidic and precipitating iron oxides and killing everything in the stream. This is a different kind of precipitate, a white material that normally what I do is characterize that kind of stuff. That's my kind of world. What trace elements is it taking up? It's poorly crystalline, it's hard to characterize, and I use special techniques that let me do that. There's also a lot of mineral deposits. This is just a map. I also wanted to mention that the reason we chose this area is there's been tons of study by USGS folks, so it's really well known. So there's tons of study of all the various mineral deposits that are there, including several of these copper resources that I mentioned, also with molybdenum here. But there's silver, we were just talking about silver mining, and there's polymetallic lead, zinc, and other types of mines. And it's right down here in the southern part of Arizona. Something got lost. So just moving into the first task of that project that I mentioned, the collaboration with Lynn Rothschild. And Lynn's been working with Jessica Navarrete up to this point, a PhD student. But as I mentioned, the project will support a postdoc. And basically this grows out of Lynn's interest in e-waste recycling and or support of the space missions. So basically, she wanted to have a way to provide, in this case, copper to the astronauts. And so the idea would be, what they have done with Jessica was introduce a silicase enzyme that dissolves silica to a bacterium. I think this is the e-waste application because the silica is supposed to dissolve something like a screen like this when you're e-waste recycling. So that goes in the bacterium. The bacterium also has engineered protein motifs that selectively bind the copper. This is the rational design. Basically, you use the principles of chemistry and go through iterations on a computer to figure out what is the best configuration to bind specific metals. In this case, copper is not that interesting, but what would be interesting is something like tellurium or rhenium or platinum group elements, these critical elements. Anyway, so you've got your bacterium and it's selectively binding your metal of interest, and then you can basically pellet it out, removing the bacterium from the liquid, and then use a 3D printer to screen print it. That all sounds like fantasy to us. We're geologists. Okay, but this first part, dissolving silica, a lot of rocks are basically made out of silica. So that seemed like a potential do. And I actually, back to the issue of gold, a lot of our gold mining in the United States is in Nevada, and there's this sort of north-south trend called the Carlin trend. And a lot of the mining in the north part. In the southern part, it turns out that it's really hard to mine that gold because it's been overprinted by silica-rich solutions. So something as simple as just being able to selectively dissolve the silica could totally open up the southern Carlin trend for mining, for example. So this is all just this hasn't really gotten started yet. We're just getting the postdoc search going. So this is not really started, but this is what Lynn has done with Jessica so far. This is sort of an overview of the whole project that kind of includes the selective resins. We're thinking that we would use the material, the selective binding protein motif on a resin, not in the bacterial form. Again, that was Lynn's design for space and what have you. But our task 2 involves basically understanding fundamentally the role that microbes and minerals and plants are having, it turns out that there are microbes that live inside plants, just like our bodies are almost, quite full of microbes, as you know. So are plants. And these plants confer a lot of capabilities, either just growth, helping them to get phosphate, or growth hormones, a whole lot. This is a whole new world of exploration that John Freeman knows a lot about, and other folks. So we're basically going to this area in Patagonia that's a historically mined area to find plants that have adapted to the mining soil. All the soil in the whole area, so remember we talked about a mine is one site, but the whole deposit is enriched, okay, just not economic, but plants have had to learn to tolerate it. So we go there, we find some symbionts, some bacteria that can live with plants, and we bring them back to the lab, do studies, testing how we can get them to grow. A lot of times compost is added to these tailing sites to sort of stimulate the soil production. And then other details that you all, I'm sure, are not very interested in, because you don't do that kind of micron scale stuff, you're kilometer scale. So again, the intrinsic connection, and that we're still working on getting our official documents, the cooperative research agreements and stuff like that in place so that we can work this summer. But basically, some of you may know that right here on campus, there are these poplar trees that have been, Intrinsics has planted to help with your trichloroethylene contamination problem in the groundwater. The poplars, the inoculated poplars here have been inoculated with a special mix of these bacterial endophytes that John Freeman and his collaborators have come up with. Sharon Doty, the lead author on this paper, she's at the University of Washington, and she's his main collaborator. She's been isolating these bacteria from trees, but they can go into any plant. That's the wild part. So she got them from poplars, but they go into anything. And here, they have specifically put in a bug into the poplar tree that degrades trichloroethylene. The important thing to know about trichloroethylene or tetrachloroethylene, anyway, there's 3 or 4 chlorines on it. And as you take them off, you produce other, more toxic subvariants. So vinyl chloride is one of them. That's really nasty if you take off 1 or 2 of the chlorides. So you need to take it all the way to CO2 if you're going to do this. And so that's what their bug does, or their group of bugs, a consortium of bugs. And you see there that the controls, which haven't been inoculated, aren't very happy. So basically that's just one of the things we want to do with them, is use the same kind of bugs on our sites. But there's some other, they're also into phyto extraction. In fact, John Freeman got his PhD studying nickel hyperaccumulators, and we'll come back to these in just a second. They're my personal favorites as well, because they also take up cobalt, and cobalt's one of these critical elements, so we keep coming back around to the same issue. So really hope we can work with these guys. Now then to the over to core proposal and the stuff that we're doing on that. Some of the reasons why, I just threw up a bunch of stuff here. That's some of the reasons why we got into this. I have a long history of studying the environmental problems related to California's historic mining. This is just this front slide of a talk that I gave at Goldschmidt conference in 2016. American can't quite make out, but there's some off-road vehicle folks that are riding up this hill, and it's kind of dusty. That's just all tailings. There's a whole bunch of people standing up here as well. This whole hill is tailings that are about 7,000 milligrams per kilogram arsenic, and that's a lot of arsenic. The background arsenic in soil may be from 10 to 100, depending. So there's several, they're just breathing that in. That land was on Bureau of Land Management land down in the Mojave, in the Randsburg area. You know that area? It's been closed, but there's lots of debris, mine tailings out there. So that's one of the reasons why driving some of the stuff that I'll talk about. Some of the other things that I've thrown up here are, the USGS has these data sets. We have tons and tons of data. I think, Adam, you put it in the proposal well, our ability to gather data just hasn't kept up with our ability to analyze it. We just got all this data. There also a lot of it here in California. California has a certain type of rock that can host nickel cobalt laterite mineral deposits, as well as potiform chromite deposits, and is related to these other type of deposits, platinum group element, that's PGE, nickel chromium deposits. So these were all motivators for us to study the two topics that we did. One of them relates to the historic mining, the other one relates to a certain kind of rock and soil that's important for California. So same thing you saw again, these are just some more news clippings, homes actually being built on top of mine tailings. This really did happen in the Mother Lode area. I did also a lot of work in Bangladesh. This is a poster that I gave a talk at the Synchrotron Radiation Lab, Stanford Synchrotron Radiation Lab, which is associated with SLAC. So I knew a lot about arsenic, and my colleagues have worked a lot on mercury. So together we knew that you needed arsenic in the past, or you needed mercury, excuse me, to get the gold out. Okay, that's why mercury is related to gold. Arsenic is related to gold simply because it just naturally occurs with the gold, sadly, for us. So most of these dots on this map is a combination of two different gold mines, I guess, on here, placers and hard rock. But all the hard rock mines have arsenic associated with them. So what Adam's been working on is basically a risk map for mining debris flows that could be related to extreme events. We already know about, well, I'm just leave it like that, and I'll try to explain. What he's done so far is take just the gold mines of California, and we just split out an area near Sacramento here to look at. And using elevation data set and making some calculations of slope and aspect, he's basically calculated where from each mine site material would move. We don't know if there's debris there. We just are calculating sort of where would it go down this drainage, okay? And then we're asking if Adams color-coded these blue lines as the direction of movement. So some of the moves are very small, some of them are large. And then we had this color coding where the warmer colors were when we were adding mines into the same drainage. So that was the first step in sort of doing a risk calculation, would be if there are more mines in a drainage, there's more likelihood that there's more material there. There's a whole lot more different types of weighting you could apply, of course, like how big was the mine, how much mercury is the main problem. I mentioned it's really mercury and arsenic are the big problems here. So right now, most of the work, I'll show in a couple slides, has been focused on mercury. People have really been kind of ignoring the massive amount of arsenic that can be associated. But for the time being, if we know, and we do know, like two different types of mines, placer gold mines would have been mercury mined. Mercury would have been used for most of the extraction. They did use cyanide when they dredged, but for a hard rock mine, it's going to have arsenic. So we can already make that distinction. I think we were talking about that, Adam, just adding one weight for arsenic as another risk factor, or hazard, sorry, not risk, hazard. Arsenic is another hazard on the mine site. But again, like we have, the USGS has data, not just where the points, these points of the mines are, but what kind of mine, when did they start, when did they stop, what, kind of processing did they use. There's just tons of poorly organized and used data. So we're trying to do that. But we're not the only ones. So I mentioned that other folks are doing this. This is a recent 2016 paper by my colleague Charlie Alpers, who, if we go any farther with this, you'll probably know about. He's in Sacramento, not Menlo Park, but he recently joined the minerals program, and he's been working on this stuff for a long time. So I've told him about everything that's going on here, and he will get involved, actually. So, but this is something that he recently did, predicting fish mercury concentrations, basically by considering how many mines were in a certain drainage. And he came up with this whole nice regression predicting mercury in these 5 species. It's a function of length and location. He considered different variables and found positive correlation, of course, with the number of mines, with deciduous forests, and with urban areas. He did it on watershed scale. So this is sort of the Yuba River watershed. Yeah, Yuba River watershed, which is one of the worst impacted I'm not sure if it's just this guy. The color coding here is this guy's the worst impacted in terms of a mining influence factor. So this is one way of trying to do a spatial analysis. But again, he's only focused on mercury as a hazard, and only focused on gold mines as one kind of mining. Another colleague of mine, Jim Raituba, has been pursuing this thing that I've mentioned a couple times, which is what's the probability of an extreme event moving mine debris that heretofore has been sitting in place, even through 50 and 100-year storms. And the argument for that is basically this. During active mining, the river streams transport capacity is exceeded, and you basically start to create this braided floodplain. And there's a lot of evidence from that, from historic photos. After mining stops, the channel starts to cut its way back through this stuff as it normally would, down to its whatever baseline, and starts just doing its thing. And but all this material that has accumulated is mining debris. And then that's what could be moved down at the bottom as what would happen in an extreme event move. So here's the challenge, is basically to estimate how much of that stuff is actually there. And so, as I said, we're not really doing that in this little exercise that we've done so far. In fact, we're sort of saying what's happening just before the floodplain. We're basically post-mine and pre-floodplain, which is an interesting place to be, actually. Talking to Charlie, he's kind of interested because we're not exactly doing what he's done. And there are these various types of mines with the high potential to have a lot of that debris. A lot of them we've already talked about, but what I didn't mention, because I'm a doofus, is that there's a whole lot of mercury mines in California. Mercury itself was mined here. Not only was it used for gold extraction, back up one, over here, basically the mercury mines are all over here. I didn't include that slide because there's too many slides. But one of the reasons the gold rush happened was because the mercury was right here and could easily go to the other side of the valley and be used. So mercury mines themselves, you can imagine, are even nastier than the mercury that was used at the gold mine. So anyways, we definitely want to add them in. These are the ones that we want to do. But folks that I've been talking to about this are basically saying, oh, you need LiDAR for that, and we don't have LiDAR everywhere. And so the question is, do we really need at that scale to be able to do this or not? My colleague Jim is saying, well, no, sort of an argument. But there's a research question, and an important one for California, because we all know about the climate change and the prediction for more extreme weather, especially storms. So switching now to the other thing that Angela's working on, and that's a state map of serpentinite soils. Well, what the heck's a serpentinite soil? Well, it's a soil that develops on a serpentinite rock. Well, what's a serpentinite rock? It's a kind of ultramafic rock, which is a rock from the ocean crust that has a certain chemical composition. It's high in iron and magnesium, and also some nasty ones like nickel and chromium, but also resources. Nickel is a resource, and as is chromium. Some things that are nasty are also resources. Serpentinite itself is an ultramafic rock that's been altered a little bit, and basically contains some minerals like asbestiform minerals, including chrysotile, the actual asbestos-causing mineral, but also lizardite and antigerite, which are two very similar. They're so hard to distinguish by all the methods that we geologists use. They're really hard to distinguish except for by transmission electron microscopy, but they're all in serpentine rock, which is actually our state rock, by the way. We have a lot of it. This is actually a map of the known, the black areas on this state map are areas of ultramafic rock outcrops. Okay, so mostly you get these kind of serpentinite soils. They're going to definitely be associated with these black zones. Even though it doesn't look like much of California, California has more of this type of soil than anywhere else in North America. So it's a very special issue for California. And I didn't put it, something like 10% of the known plant types in California are endemic. They only occur on these serpentinite soils. Because of the unique chemistry, they force a specific vegetation type, which was initially something that Adam and I were, that was one of the initial interests of our proposal, because Adam has worked on vegetation, and we were interested in seeing what that unique signature would be. Basically, a lot of plants just can't grow on this stuff because it doesn't have nutrients. But what plants do adapt to grow on it, they're very specific. These rocks also contain mineral deposits. I mentioned quickly there. They're not that important in terms of what we call world class. They're not big enough to be considered economic. But if we're talking about, so the laterites, for example, I mentioned really quickly the nickel cobalt laterites. Again, they're not economic for nickel, but if cobalt is a critical element, perhaps we just mine them for cobalt. There's but there are nickel laterites up here that extend into Oregon. So again, I'm just saying all these things kind of repeats, but our drivers are to find these critical elements, and this is one of the motivators why we're doing this. Can we pick out, so this is back to the exploration part, these deposits occur in these serpentinite rocks. Can we use our geochemical data sets and remotely observed measurements to pick out these deposits? Will they pop out by chemistry or geophysics? The chromite deposits are quite dense. Unfortunately, it turns out that the whole rock type is very dense. So in this, usually we use geophysics to pick out a dense or magnetic mineral deposit in the subsurface from the surrounding rock. But that doesn't work in this case because everything's dense. I just wanted to mention, I happened to find this paper. It's a really old paper, but it's about management of vineyards. And there are some vineyards on serpentinite soils. This is an image that I grabbed off of, I'm talking about 280 somewhere in Santa Cruz Mountains. And there's recently, I don't know if any of you saw it, but there's a lawsuit going on right now. Last week it hit the news around arsenic in wine. Some of the cheaper white wines, like your Trader Joe, Charles Shaw, Two Buck Chuck, they are alleging that they knew there was arsenic in that wine and they didn't do anything about it. So this is kind of a joke, but it's a real thing. I've not heard of chromium in wine, but the nasty form of chromium, there's two forms basically that you have to worry about with chromium. And it is, the carcinogenic form is very mobile, and it certainly could be dissolved in anything. That's not really the reason we're doing it, but hey, sounds fun. Oh, I forgot to mention, there's no map of the soils. This is a map of the rocks. There's no one map. It doesn't exist for the whole state at a scale that you could use for land management. Land management is why we need it. I mentioned the carcinogenic part. It contains chromium. It is suspected to be a source of chromium in the Sacramento Valley, in the groundwater, where there's elevated chromium. The asbestos minerals, they're an issue for Caltrans. I heard a talk once when they're doing a road cut, when they want to decide where they're going to make the road. If they hit some of this type of rock, whoa, we've got to go measure for asbestos. You know, it's a safety issue for them. Landslides, the type of minerals it contains, and because it doesn't support a lot of vegetation, it just easily slides. I live near Edgewood Road, near Redwood City, and that road goes up to 280, and it's just passes through serpentinite, and it's just a mess, just coming down everywhere. So, and that was the issue with the ag issue. Sorry, I'm kind of jumping around. But anyway, lots of reasons for a state map. Oh, Adam did find a state map, a county map. Santa Clara County has a map of serpentinite soils. And I found something that I didn't get on here, one area of a state park they've mapped out. But, you know, we need them everywhere they are. So here's what Angela's been working on. It's been fun. We've just been digging around and figuring out all the data USGS has. And she's found lots of data for the mines and soils. I showed you some of the where we've been finding this stuff and categorizing them again, you know, by what they contain. And then she's been doing a training network to classify these images. She's got this accuracy. I haven't been able to talk to her because we haven't talked about this since I was like, here, data, go do stuff. A lot of this has been finding out where the data are and what we want to do with it. And now she's working on the image segmentation, which would be something like this. Would you like to make a comment about it?
Sure. So the previous slide was about trying to classify the images. So the training data set was based off of Landsat 7 spectral images, and I had, using the previous slide, figure out what points were probably serpentinite and what points were probably non-serpentinite. And using this data, I extracted parts of the Landsat 7 data to put these images through a convolutional neural network and try to learn pattern to see if there is anything in vegetation or anything in the spectral data that could tell us whether or not it was a serpentine soil or non-serpentine soil. So I tested this on a test set of 1,000 images, and I was able to get around 87% accuracy on it. Following classification of serpentine images, the next step would be to see if I could try image segmentation so that we could pass in, for example, the image on the left and get something like the image on the right, where we can say, okay, this area is this pixel is probably serpentine, or it's probably non-serpentine.
So, at the end, we're back to this. I think this is really the area where we can do a lot, and I think these are the things that we can do a lot with. I've mentioned a lot. Preventing these mining-related disasters. And this is more than just in the United States. I didn't really get to hit on that, but I mentioned in the abstract that we do have sort of this world purview. I'm working in Puerto Rico right now. I'd love to do just what we're doing with Adam, with the risk mapping stuff in Puerto Rico. They have some historic mining areas and some real water issues. But the issues of tailings dam failures, I didn't get to mention it, but I worked at a Superfund site here in California that was a tailings dam failure. It was an old log dam, and it really caused a lot of problems. So we can find those, and we can stop those things from happening. The extreme events I mentioned, being able to observe. I was really interested in the Porphyry site, and I went there, and they were saying that we're going to be able to observe ecosystems and describe their health in ways that has never been able to be done. And so being able to, it's a big thing that we worry about, is how to set what we call baselines and backgrounds. How do we know what an area it's mineralized but it's never been mined, that soil is going to be elevated in certain elements. If the mining company comes and they do their thing, when they reclaim it, we can't ask them to put it back to something that was, zero. What do we ask them to put it back to? So being able to do this ecosystem health assessment with vegetation or remotely, some of it's ground-based, but some of it's not, and being able to monitor before, during, and after, that would be really great. Then sort of these more, down-to-earth aspects that I mentioned on the other project, with phytoremediation, phytoextraction, and biology-based technologies. Those are really some areas that I see that we could do some work. So, thank you.